Well, here are the answers to the problems in thermodynamics, and this is only for the 24-25 or the university physics students. TH and TL should always be in Kelvin. And remember that the coefficient of performance of a heat pump is TH by TH minus TL. But for a refrigerator, it would be TL by TH minus TL. That's a very important difference. Get 8.25. That's for a heat pump, and that's why it's TH divided by TH minus TL. Again, if it's a refrigerator, the COP would be T of the low, that is TL divided by TH minus TL. And the second one, you're asked to find the change in entropy. First, you'll have to find the common temperature reached using heat lost by the aluminum is equal to heat gained by the water. Where X is the final temperature, and you see how I get the 921. It's 0.22 calories converted into joules, multiplying by 4.186, and then multiply by 1,000. That is supposed to be 1,000 there. Calculate. Bring the X terms to one side. And then you get the final temperature to be 22.43 degrees Celsius, which is 295.4 Kelvin. Now we got to find the change in entropy using ds as dq by t. On the other page, change in entropy of aluminum. It's mass times specific heat times difference in temperature. See, remember that the difference in temperature in the numerator could be in Celsius, but in the denominator it has to be in Kelvin because it's not a difference. And again, in the denominator we're taking the mean temperature or the average temperature. Now, since heat is lost by aluminum, it's negative 41.06. In fact, the numerator here would be the same as that for aluminum because heat lost is equal to heat gained. And in the denominator, you have the average temperature. So this is positive because water gains heat. Therefore, the net change would be I think I made some mistake there in the calculation, so it was supposed to be 164.5, negative 164.5. Here again, some problem in the calculation. When I put it into the calculator, I apologize for that. So you get 172.9. It's positive because heat is gained, and then the net change is 172.9, take away 164.5. which is 8.4 joule per Kelvin. This is number 3. It's the same kind of problem, so not going to explain that, except that the difference here is because the quantity of water is so large, the final temperature is going to be 10 degrees Celsius. So you calculate the change in entropy of lead, which is negative because it's losing heat, and then find that of water, which is positive because it's gaining heat. And number 4, it's a direct question, but efficiency must be taken as a decimal, so it's 0.35. Rearrange and calculate the temperature of the cold reservoir. (325 Kelvin). Number 5 is straightforward. (455 Kelvin). Number 6 is just knowing that work is QH minus QL, and the question says how much heat must the coils discharge into the kitchen, which is obviously QH. So (630 joules). And 7 is again about a heat pump, and remember the coefficient of performance for a heat pump is TH by TH minus TL, but you get it as 1.6 because a Carnot heat pump has an efficiency of 1, and then 60% of that is this, so take it as 1.6 to give (112 Kelvin is actually in Celsius negative 161 degrees Celsius. Don't worry about this problem that much. Number 8, you got to remember that specified constant volume for a gas is 3 by 2. If it's monoatomic, it's 3 by 2R. And dq is ncv dt. So ds is dq by t, and that is ncv natural log t2 by t1. Well, I'm just trying to show you how you get that formula when you integrate. So that's given us 200, so rearrange and calculate. There is obviously some calculation there you have to be careful about. I'm saying that I did not even use the first part. Number 9 is again similar to so many questions that we did. First, find the final temperature by using heat loss by the hot object is equal to heat gained by the cold. Again, I'm showing you how you get the specific heat in joules per kilogram Kelvin. Be careful about the calculations, collect the x terms and then divide. Now change in entropy is dq by t. Where did I get this 40,584 from? I just, it's just one of those. Both are equal, so either this or this one would give you 40,584. That's the quantity of heat either lost or gained, divided by the mean temperature. So that gives you 123.92. And the entropy gained by mercury, same way, is the same amount by the mean temperature of mercury. And to find the net change, just take the difference between the two. Actually, you're adding them, you get 8 joule per Kelvin. The 10th one is you're given the temperatures and the quantities of heat taken in. You have to find out how much is given out. So just know that TL by TH would be equal to QL by QH because of the two formulas for efficiency. Rearrange QL and make it the subject and calculate. Remember, this is still in kilojoules, so the answer will be in kilojoules. The 11th one, the change in entropy is given, so you just got to remember that heat required for ice is mass times latent heat. So you get the mass as 492 grams. In 12, temperatures have to be converted into Kelvin and just calculate. It's 45%. 13 is a very important question because here the volume is changing and the temperature is also changing. So there is a particular formula that you have to use for that. To find the total change in entropy, you have to consider the change in temperature and the change in volume, and that's why you have this formula, 2 parts. And then rearrange that and first try to find the natural log of T2 by T1 and then find out T2. It's just math after that. Remember that the final volume is 1/3 of the initial, so that's why it's 1 by 3. Down here it's 1 by 3, and then I'm showing CV is 3 by 2R, that's why I got the 12.47. you get T2 as 1390.72. Oh, that's supposed to be Kelvin. Not joule per Kelvin. It's supposed to be, where is that? It's supposed to be Kelvin. You just find the changes in entropy and find the net change in entropy. Just like in the problems before, you get 0.2214 joule per Kelvin. Work is simply QH minus QL. This question is about an ideal heat pump, and the coefficient of performance is TH by TH minus TL because it's an ideal heat pump. If it was a refrigerator, it would be TC by TH minus TL.